Let me introduce to the audience who is Elma Durmisevic. Elma Durmisevic is a researcher, architect, practitioner, architect also. She has a PhD from Delft University, and her private office for the architect office is in Netherlands. And her research actually engages with circular economy, reversible buildings, and transformable buildings. And she was a coordinator, if I'm not mistaken, the BUMP project, which was a materials as building bank project for EU project, which had a very positive influence on the profession. And we have been reading about this result of these projects and publications. So she was so kind to accept our invitation. Without not extending too much, I will give words to Elma to give a presentation about digital twins and
reversible BIM.
Reversible BIM, yes, I have to remind myself. Okay, the word is yours, Elma. Thank you.
Thank you very much. It's great to be here. I'll share my my screen now. See if that works. Can you all see my screen?
Yes, but not yet. Now we can see it. Yes.
Yeah. Okay. So thank you very much for presenting me to the audience. I will go directly to the content of today's talks and discussion, and I wanted to share with you some ideas on decoding circular capacity of buildings and its materials, and in particular the role of digitalization and digital twins, which can help us to move further from where we are, or to speed the transition towards circularity and circular buildings. And I will be later on focusing more and talking more about the reversible BIM, which you see here, which is a tool I developed a couple of years ago, but it has been also validated and tested during a European digital deconstruction project, which we use to develop digital deconstruction platform for supporting decision-making around deconstruction and reuse options of existing buildings and materials. To start with, I will not talk much about why are we doing all of this, why circular buildings are important. Just put some important lines to refresh our minds, and how important the built environment is, and the buildings, and how important it is. How do we design and plan cities and buildings? As we know that through buildings and cities, we manage stocks and flows of natural resources. And the fact that we have these kind of maps now coming from the World Bank, mapping the resource footprint of the planet, how much of the resources are left for general consumption, illustrate that we are not managing our stocks and flows of resources through our buildings and cities, which are the greatest consumers of the natural resources in general, saying that there's this map which illustrates how many resources are used per year, per country, and mapping the resource use against the capacity of the country itself to support these resources. Countries which are colored in red indicate that they use 4 times more resources per year than they have within their own borders. What is actually pushing us all on the planet to move much faster towards circularity and circular economy are exactly these maps, which are becoming more and more red. That means that there are less and less green countries, which have some leftovers that we can all take for our yearly consumption. So obviously the way and a linear approach to use of resources, natural resources, is not bringing us very fast. And of course, next to that, we have the whole discussion about the very negative impact of such approach to the biodiversity, climate issues, climate change, pollution of water and air, the great amounts of waste coming out, which need to be sorted out. And just to illustrate, again, I'm sure you all know all these figures, but prior to further slides, how important built environment is and how important building industry is and how big impact it has on the environment and on everything that they care about these days. And this is summarized in the figures down, which illustrates the results of the way how we design and build buildings and how we manage buildings and building materials throughout their life cycle. And we manage them in such a way that in the end, we end up with 40% of CO2 emissions in the world, which is building related, 50% of material resources taken from nature are building related, and 39% of natural waste production is related to the building sector. So obviously, a very important sector that needs to think very hard and fast how to transform itself into a more effective sector with respect to the way how it impacts the environment and the other ways of living on this planet. In fact, when we summarize the situation as where we are as a profession, engineers, architects, planners, there are two key tracks that we need to take into account in the future. One is to understand, for the short term, to understand the capacity of existing buildings and how we can effectively reuse buildings or materials out of these buildings in a new ones and new products. And the second track is about the specifying standards for new circular buildings and how the future circular generation of buildings will look like. So in that respect, I wanted to stress again just on these two lines, on the line on the specification of future standards, how our future buildings, which are future-proof buildings, would look like. We need to move from the approach of design for demolition, which is the one which we still very much globally have on our design tables, to design for reuse and reconfiguration, which will steer us to design of real circular buildings, which are transformable and adaptable and made of exchangeable and reusable elements, which can be reapplied in another buildings or other products in the future. A second track, as I mentioned, to understand the reuse, how we can reuse materials from existing buildings, to understand the capacity of existing built environment, existing buildings, and how the feedback loops could be organized so that they become shorter and shorter. The shorter feedback loops of materials from along the whole life cycle of the buildings will result into a lower environmental and economic impacts of these operations. So I'll just run further through these two concepts, a bit elaborate more on them, what one or another means. This is the first one. Shifting the design for demolition to design for reconfiguration would require obviously a new design approach, where we would be looking towards different organization of our built environment and buildings, where we will not be talking about demolition in the future anymore and new construction, but mainly about the upgrading of the environment and built environment in general, and obviously hopefully living in a world where demolition would be seen as a design mistake, something which is definitely not going to happen and not going to be valued in new systems. That approach needs to adopt this new understanding of what the capacity, multi-layered capacity of building is to provide circularity on different levels. And there are three design dimensions which I identified a long time ago, but I see that they are very much recognized nowadays. So the three design dimensions that we need to take into account when designing new future buildings is to take into consideration the long use of buildings. That means that they need to be adaptable. They need to have a capacity to modify themselves and adapt to future changes of the users and their requirements without demolition, without using the quality of materials which are in them. The second dimension is the technical reversibility of the building systems and components, which need to be reconfigurable and transformable, reusable, so that they can be upgraded, replaced, and reused in different situations and different buildings or products. And the third dimension is the reversibility of material, meaning that we need to design, having in mind that materials need to be easily separable, so that even when they end up in recycling, the recycling and upcycling is possible. And that is a burden today, and that's why today we are mainly talking about the downcycling and not so much recycling, as in many composites in a building which do not allow easy separation of materials on a material level to create exactly the new recycled content again. These three design dimensions form the core of circular building, which have these fundaments: adaptability, reuse, and disassembly, and in a way how we as designers approach and design buildings, in particular, how we deal with adaptability, reuse, and disassembly through the design process will tell us how circular buildings that are designed really are. On the other hand, this approach is also used to understand the capacity and circularity capacity of the existing buildings. It's how adaptable existing buildings are, how reusable the content of the material in the existing buildings is something that is taken into equation that I will be talking about later on, how the same approach is used for the design, but also assessment of the circularity performance of the building. So in following this line, these three fundaments of circular building: adapt, reuse, disassemble, we can identify and classify all buildings into key circularity profiles, and these profiles will reflect how much of the content in a building can be, whether it's designed or existing, can be reused, whether a building as itself whole can be reused or not. And obviously, if transformation of the building is very low or does not exist, and it's the materials in the building are not reusable, the circularity profile would be zero. There will be no circularity in this building. And obviously, the way of the assessment goes further, that as we improve the design or when assessing existing building, transformation of the building turns out to be higher, and the reuse potential of its materials goes up, the circularity profile of the building goes also up. In order to design such reversible buildings, as a designers, we need to look into number of dependencies that exist in a buildings, so that will allow the transformation and reconfiguration and reuse of individual parts or building itself. That means that we need to understand and design the functional independency, so that all functional elements in the building can be independent of each other, can be exchanged easily without having impact on the surrounding elements with different functions. That we, from technical point of view, need to design technical independency of all physical elements in a building, so that they don't form a kind of spaghetti relations between each other, but they have more structured relational diagrams, which would reduce the number of connections between elements, reduce the complexity of assembly hierarchy of these elements. And the end, physical dependency need to be replaced into physical independency by the way how we design connections and relations between the elements. So that's obviously the design task, but at the same time, this design aspects being functional independency of elements, technical independency of structure, and physical independency, turns out, if we want to assess the design solutions and performance of design with respect to the circularity, these aspects become evaluation criteria and help us to assess the circularity of buildings for design solutions. And that's how the tools and digital twin that I will be talking about is working, and how it's assessing the circularity and reversibility of building and reuse potential of its materials. And this assessment is being done on a building level. Obviously, as I mentioned, these 3 dimensions, there are also 3 levels of assessment. You can assess the reversibility and circularity on the building level, on the system level, and on the part level of the building. Then moving to another track, which I mentioned is also a very important one, is being to understand the capacity of existing buildings to be reused and their materials recycled and upcycled. This is very much exercise that we are heavily involved here in the Netherlands, but I'm sure across Europe and beyond, to understand what the existing buildings can do, how they built up, and how easy can parts be recovered, how feasible from financial point of view or also environmental point of view these operations are if we want to use the materials from existing buildings into new ones, and how can we identify and define different reuse options that materials from existing buildings have, starting from direct reuse, which would be the most beneficial, but obviously as these buildings were not designed to be disassembled and recovered. Those are the most expensive operations. In this case, reuse by remanufacturing of parts, or recycling by creating aggregates of some parts of the building. So I'm showing here also some examples from a big case project that we just completed in south of the Netherlands. It was called Çolakoğlu, where we tested 9 deconstruction and reuse strategies for existing buildings in order to understand their capacity for reuse. I don't hear something in the background, so I don't know if that's okay. That's sorted out.
Some background noise. Please turn off your microphones, the audience.
I think it's sorted out. Thanks. So those are these 2 tracks I was talking about, and then we come to the digitalization, where I would like to talk about the reversible BIM in the form of digital twin, which can help to address both of these tracks. On the one hand side, design circular buildings, do the assessment of design solutions, and on the other hand side, assess the capacity of existing buildings and understand which parts of the existing buildings do have reuse capacity, and which elements can be reused, what their environmental and economic impacts would be when doing so. And then I come to this, also a bit more of explanation of how the reversible BIM is looking and assessing the reuse potential of materials within a building, which are then modeled and digitalized. It does so by looking into how easy elements can be taken out without damages to themselves and damages to another, causing damages to other products, and how short the feedback loops are. I mentioned the shorter feedback loops, the higher circularity profile and higher reuse and transformation capacities. And that's also reflected in environmental and economic impacts, because if you have a shorter feedback loops, that means you need to put less effort, less hours, labor hours, but also less energy and transport in bringing materials back into the use sequences. The longer these feedback loops are, as going back to the recycling of a content, the more costly these operations might be. When just trying to understand the how easy elements can be taken out and how that can be assessed while using the digital tools as reversible BIM, the key challenge is how to understand the relations between elements and how to simulate them in a digital environment. As we need to understand all the number of relations that each element has in a building in order to be able to analyze these relations, in order to be able to understand the type of connections of these relations, and also to understand the hierarchical position of each of these elements in a building. So in general, the use of reversible BIM to design building or to assess the reversibility of design solution or the reversibility and use potential of existing materials from existing buildings has these 7 steps, which I listed here, starting from the data collection, which are drawings in the time when we are designing buildings, digital drawings then and digital models. But if we deal with existing buildings, then those are primarily would be nice to have a point cloud files. As the building is scanned and point cloud files are created, which are then used to recreate the digital twin of the building, so that it can be used for assessment of reuse potential and circularity of its materials. And that starts with the second phase, which is about the data processing, where the product coding and BIM template is being used so that BIM plugin can be implemented. And I'll talk more about the Revit plugin in a sec. Just what is needed, what was needed, which functionalities needed to be added to Revit in order to enable this digital assessment of reuse potential from whether existing buildings or new design solutions. And then there's Revit to Excel, an Excel to Revit exercise for additional calculations if needed. The color coding, you already saw, the color coded images, which are automatically generated based on the assessment of those dependencies, the number of connections and types of relations, the hierarchical dependencies, the remaining technical life, and so forth. Based on this calculation, the color coded is being, in the end, assigned to all materials so that you get a geometrical and graphical representation of the circularity of your building. The more green the colors are, the higher use potential. It means less effort, less costs, less environmental impact. The more red means more effort, more costs, and higher environmental impacts in general. The reporting in the end comes of reversibility, including reuse options of materials, the deconstruction steps and embodied values in terms of CO2, which can be avoided, the raw materials which are avoided, and the waste, which is also avoided by certain levels of reuse potential and circularity profile. And in the end, for the materials which have high reuse potential, a BIM object library is created so that architects can pick up the information about, if we are talking about the existing buildings, of materials which have high reuse potential and can use these materials directly in design of new buildings. So when talking about the existing buildings, the only difference between existing and new and use of a reversible BIM for existing buildings or design is that the first step, the data gathering, where the data comes from to build up the digital twin. And when we talk about existing buildings, the data ideally comes from scanning and from these kind of 3D point cloud files, which are then transformed into the first digital representation of the building, where during the modeling, it is important to keep in mind that all elements need to meet each other so that the interactions between elements can be identified and analyzed. And if that is done properly, then they would get this kind of relational diagrams to check whether the relations work and whether all elements are properly modeled. And that means that we will be able to assess the number of relations that all elements have within each other. Based on that, also the color coding is made. And also further on down the road, we can assess then the type of connections that each of these lines representing relations would have, and the dependency in assembly and disassembly steps. And this is the color coding, which in general comes out automatically once everything is being done, properly modeled and done according to the reversible BIM protocol. Now, some things that I want to go through that needed to be added in Revit as part of the plugin, because Revit was not supporting these functionalities, and other BIM software as Autodesk, for example, also has the same problem. And the thing is that in assessing the reversibility and circularity of building materials, it is very important to identify functions and sub-functions of elements, so that elements can be grouped as functional groups to have better overview of the functional dependencies, but also on sub-function level. So what you see here as an example is that, for example, for the roof layer in Revit, there is only a roof category. There's only one category, but it does not, this category does not make difference between a roof finishing layer or a roof insulation layer. So it's all named as a roof, while finishing and insulation are the functions which are kind of main building functions presented in reversible BIM. You see that also in a facade, for example, for facade layers, as plaster, as written here, faster panels, a mortal Revit has only a category wall. So there is no distinction as a load-bearing wall or partitioning wall. So this functional distinction, whether a wall is load-bearing, has a load-bearing function, or it has a partitioning function, which is the case, for example, often also inside of a building, that's not present in Revit categories. Or within a facade, for example, we all know these glazing facades with the glass systems, which have steel profiles, horizontal vertical profiles with different types of profiles. Where Revit classifies horizontal and vertical steel facade profiles as structural load-bearing elements, while they do belong to the main function enclosure of the building, and they do not have the main load-bearing function. So those are primarily reasons why, in the end, I had to decide to build in additional parameters, which I call the reversible BIM parameters, bringing in Revit this main building functions, so that when modeling all elements, the functions, the main building functions, can be assigned to each element in a model, so that there is no confusion further down the road when assessing the reversibility. There are some other additional parameters that needed to be added, as the reversible BIM is assessing also the embodied CO2 in materials, but also avoided CO2. If materials is used, how much CO2 can be avoided by that action, the hazardous materials, whether they are there or not, and also the remaining technical life cycle of material, which plays important role in the durability of material itself. This information is not present in existing BIM modeling software. I developed the additional reversible BIM material database, which is based on ACE database of materials, and then added the CO2 calculations based on their density and the technical life cycle of materials, which comes from the Dutch catalog of technical life cycle of building materials. So this material list is then added as the main material list to be used in the reversible BIM when working with Revit or other BIM software. And by choosing, for example, as here, the insulation, which is rock wool, and insulation part, that is insulation material, all other information is being picked up automatically and helps with a later calculation of reuse potential and environmental impacts of the results. Additional part, again, which I want to mention, I will not go through all, but just the important ones. Connections, obviously, in order to assess how easy elements can be taken out without damaging surrounding parts or themselves, the connections will play an important role. The number of connections is important to understand how the deconstruction process can be organized, and also the type of connections, as all of these lines, which represent the relations and connections basically between elements in a building, they need to get their, they are being analyzed, and basically each of these relations gets its type of connection, which comes out of this table. All connection types are listed from reversible to irreversible, starting from gravity force connection, which is the most reversible where there is no damage at all, and going down to the material strong connection, which is stronger than connected material, connected part, which basically cannot be dismantled at all. And this is being added then also when modeling the, as for example, the blue element here, which is a concrete block in this wall, indicates that that element itself, it's a double wall, it has in total 9 connections. And I just illustrated because very often, if we would just see a block or a brick in a wall, we would never think that it has 9 connections. And that's why this tool as reversible BIM helps a lot to really be very realistic and gives a very realistic picture of what is happening within a building and what are we really dealing with when preparing for the construction and recovery of materials to take them out. So I'll just run through a short example, shortly through a couple of steps of using reversible BIM. Here, looking into existing building, this is a train station in France, in Fallujah, I believe Fallujah, which needs to be deconstructed, and this tool was used to do the digital inventory of the materials to understand which materials could be reused for some other buildings in France. So first it was scanned, and then first digital model created, indicating that there are 465 elements in the building, which is going, part of the building which is going to be demolished, and showcasing the pattern of relations, where the red elements in this pattern are elements which have more than 7 relations and would be difficult to take out without damaging. And the green ones have less than 3 relations. So this is an overview which just gives an idea about the number of connections that elements have, and the red ones have the are the ones with the most relations, and the green ones easier accessible. Then in the process of modeling, the elements are being selected, and when selecting in the drop-down menu, the type of connection is assigned, which has a coding, as you can see on left-hand side, the coding of all types of connections from reversible to irreversible, and they are coded from A1 to D4. So when there are standardized buildings and standardized with standard connections, and all elements which have the same position and connection can be selected at once, and the connections can be then assigned also at once, which speeds up the process of assigning these connections. And then also the assembly sequences, which are very important, are being listed based on the relational diagram, which I have showed in the first place, which indicates which elements are assembled first and which after them, so that the dependencies in this assembly can also be analyzed, and the accessibility of individual parts and products can be analyzed. And also the overview of what you see here in upper two tables are the overviews of connections that one single element has. And those are connections which are called to the element and connections from the element. So the first table is connection from the element. That means an element which has an ID 906063 is assembled, and then after it has been assembled, 4 new connections have been created with that element due to the later assembly and next assembly of the building itself. And then there is the other one, which is the illustrates the connections to the element, and those are the connections which were needed in order to install element itself in a place. So there is also distinction. This distinction is important to understand as the dependency of the accessibility of a dependency of the element in terms of its accessibility and hierarchical position in the structure, and how easy you can reach the element during the disassembly. The scanning of the project of the existing buildings is usually done based using the scanners, mobile scanners, as you can see here, or the drones on infrared scanners are used as well. Nowadays, there are also robots walking through the building for some difficult parts to get these point cloud files. And this is an example of the museum, Roman Museum in the Netherlands, which I will use to illustrate also the outputs which come out of the reversible BIM. In the case of this Roman Museum, the 7,277 elements have been identified in the building. And while analyzing these relation diagrams, 36 parallel standardized assembly procedures have been identified, which is an interesting information for the companies which will be involved to recover material from the building. And this is a matrix which illustrates when steps of assembly, starting from 1, as you see here in the upper left corner, the parallel assemblies, the numbers, if you have see many twos, it means all these elements are assembled in one parallel assembly sequence, and then the next sequence starts. And this matrix indicates at which point in time the element is connected with another one, and when the second connection comes in, which sorts out the hierarchical order of the whole assembly and informs us about the disassembly procedures as well. Then the assignment of the connections takes place, identifying this the connections between all elements based on the indicators and coding which I talked about. The color coding, which indicates in the end the reuse potential of elements in a graphical view, and in the Excel sheet formats and the formats on the digital platform. Those are the outputs which are then created on material type level, the material name level. Also for functional groups, they can be organized, and basically all materials, each material in the building has its a number of connection as information, the reuse potential as information, the volume, the embodied carbon in it, the reused carbon, reused material, and these are calculated based on reuse potential score within a reversible BIM. Besides that, the overview and outputs, because there's lots of data, it can be organized in different ways, and it's very often customized based on the questions coming. Hello. Okay. So the data can also be organized in a way that all materials are listed in a building, and the amounts in the tonnages in the end, what we see here, 85.3 tons of materials in this building have high reuse potential. It means that they can be directly reused in other buildings with very little or no, not much reparation processes. And that's also listed per material as well. There's also an overview which gives an indication of how much in total of this material, how much of materials in a building, as in this case, 6,809 tons, and the percentages of the materials that can be directly reused on site. And because this building will be partly deconstructed, and some parts do have capacity to be reused again, so there are 30% of materials that will stay on spot. The percentage of materials which can be directly reused is with some small reparation and cleaning can be brought into a new life. Potential of materials for recycling and waste, and this is the amount of materials which cannot be recycled in a good fashion, and there is hazardous material in there as well. And next to that, an overview reflecting the carbon, embodied carbon in materials which can be reused on site, directly reused, and so forth. And these kind of calculations are then used to classify the circularity profile of the building. And this building we see here in Roman Museum in the Netherlands is classified in reversible building profile, circularity profile 3, as we can see 47% of material can be reused and falls into category between 40 and 70%. Basically, this kind of overview has been standardized for buildings, and I'll show more of these overviews later on of some other buildings, just to give you an idea of different typologies of buildings and their circularity profiles. But in the end, also, it's interesting to look into the circularity focus points of buildings as which basically help us to identify circularity profile as a material which can be reused, recycled tonnages, volume reused, CO2 avoided, waste produced, and circularity as circularity indicator of the building. Then when we identify the materials which have a high reuse potential, these reversibility ID cards are created as an information, some general information of the material which can be reused again to understand how much mass is in the material CO2 and what kind of reversibility stage it is. The dimensions of material so that it can be reused again, or also the waste, the hazardous waste, as in this case, where these materials are. You see here the blue ones, so that they can be identified and taken out in a safe way. For the materials which have high reuse potential, the digital library is created, providing this information about the geometry, the dimensions, so that architects can reuse these materials directly into new designs. And that is also what we are doing in next phase of the laboratory for green transformer buildings, where the profiles from this Roman museum that I was talking about will be used for the facade elements, which you see here. For the designers themselves, this is a data which is interesting when designing a building, and these outputs are coming of the reversible BIM assessment, and those are the number of indicators which tell designers which indicators might be improved in order to have better circularity of their design solution or of their products. And those are the indicators which you see here. So when designing, this is the output, which is interesting for the designers to use as a kind of a checklist of design aspects that can be improved when we see, for example, connection damage has very low score. That means that the connection type is not very well designed for the circularity. So some improvement in this case could be made in order to increase the reuse potential of the part. I'll go now through an example of the building. It's first phase of the GTB lab, where we have used the reversible BIM to the design, but also used it to assess the reversibility aspects and circularity profile of the building. This is the first phase, which has been built now. At this stage, we are in preparation of construction of this second phase, where I mentioned the steel profiles from the Roman Museum will be integrated. And we work towards this last potential theoretical view, where the laboratory for clean transform building is set up as such that we transform a building once a year, and we'll see where we'll end up in 10 years' time. So it did through the design and construction, the reversible circular building principles have been applied and used as much as possible through a number of workshops with the industry, trying to design all connections in a way that they do not leave not much damage behind. I also set up systems as such that they can be reconfigured, as you can see here, and some parts taken out, or the facade, which becomes a flooring of the terrace, or the closed facade, which can become a door, and then again floor. Because these kind of reversibilities of the system themselves are also very important when thinking about these three design dimensions that I was mentioning in the beginning of my presentation, and also the assembly sequences of how easy can you take the parts out and reconfigure and change some parts of the structure. Once this first phase was done, the 3D scanning took place for a collection of the point cloud files, and then the reversible BIM has been used to model the building following the reversible building protocol to assess all these relations, the types of connections, the assembly sequences, and generate the calculations and the circularity profile of GTB lab. You see here that this number is not well seen, but the direct reuse of elements is listed here. I think something like 30% or something like that. Reuse by reparation, 21% recycling, which is concrete, which you see here in orange, which had to be used because of the bad soil and lots of water and moisture around. And the same calculations done for the carbon, which is embodied in the materials, which can be directly reused by repair and so forth. And this is the final circularity profile of the first stage of reversible BIM, GTB lab using reversible BIM, which is now formed in circularity profile 4, as more than 70% of materials can be reused. And according to the calculations, we 79, that's in a margin between 70 and 80% of materials to be reused. This kind of design in a circular manner helped GTB Lab also to organize the special contracts with the suppliers and contractors. to take their materials back, because they are designed in a way that they can be easily taken out and without damages, and that this industry can then apply the materials again in the new buildings. And since this GTB lab is a laboratory, which I hope will not be there longer than 10 years, because the aim is to stay there until it's not more necessary, and it will not be necessary at the point in time when all buildings become circular, and I hope that will start happening from 10 years from now. So these materials will be removed after 10 years, and we managed to create the agreements with the construction industry for take-back systems, which is a very important part when trying to understand how circular economy in construction can work. And that's the, I think, the only way that circular economy in construction can work, by bringing the construction industry on table, doing things together, and they need to be also convinced that their materials and systems are put in place in a manner that they can take them easily out, and without lots of effort in their own facilities, industry facilities, they can use these systems again in new buildings. And this did bring some savings for us in the construction, during the construction of GTB lab, due to these kind of agreements, where circular building becomes then more profitable than linear building, if this is designed in a manner that the industry has confidence that materials can be taken back. So that's quite an important lesson learned from the first stage of GTB lab. So I promise you'll go through a couple of the views on different typologies of buildings and their circularity profiles. And this is the railway station in Luxembourg, which has been reconstructed, built in the beginning of 20th century. And some of materials already reused in some new buildings in Luxembourg. This is the housing project in France from 70s, with very low circularity profiles. You can see here one. Basically, all materials here have almost no value, and all the building will end up on waste disposal or some downcycling. And these kind of circularity profiles, these are other outputs that come out automatically from reversible BIM, where we could see the embodied material in a building in one column, and then potential reused content. In this case, this is concrete. If colored orange, that means it goes to downcycling, recycling. It's not very nice color to see. On the other hand, the CO2, which is embodied in these materials, and potentially avoided CO2 by recovery and reuse. So different profiles, circularity profiles with different levels of reuse content within materials, definitely having different color coding, as you can see on the left-hand side, and tell us something about the typologies of buildings which tend more to be circular, and ones which tend not to be so much circular. And this is an overview of a number of projects we've done throughout Europe, from France, the Roman Museum, GTB Lab, the historic sites in Belgium, the France apartment block, the station in Luxembourg, the reversible module on the Garden Nord block next to Garden Nord, which will be reconstructed end of this year. All of them were used to also verify the circularity profile and understand, and also the margins which you see here, which are set up for reuse and recycling, representing one or another circularity profile. These profiles help all for the regions, and this is diagrams I developed for the region south of the Netherlands, to also understand how fast they can move towards circularity, with which type of building profiles in the future they can try to reduce the carbon footprint, reduce the waste, in construction and the use of raw materials in construction. So that the profiles themselves can have a multiple. Understanding the circularity profile can also help in future planning and strategic planning on a regional level as well. Reversible BIM, just a few last slides, is integrated, as I mentioned, into the digital deconstruction platform, which we built together with a couple of partners in Europe. This platform brings together 4 individual modules. The one is 3D scanning of buildings, then the reversible BIM being the digital inventory tool. Then once the elements are identified as material with high reuse potential, the material database is created, and with the help of blockchain technology, these materials are then connected with sales platform. And primarily, goal of this platform is to support decision-making regarding the reuse options of materials, reuse strategies, and the construction strategies of existing buildings and their materials. Just geometrical representation of what I just said, from scanning to the database, and the final slide with the knowledge platform, which we built up for circular building knowledge platform, where the digital deconstruction platform will be placed within, also with the navigator, how to navigate through the platform and the tools. This will be my talk for today. I hope I'm just in time for everyone who has to leave to be able to leave. Thank you.
Thank you very much, Elma. It is a very vast subject, but it's mind-opening, I should say, for us. We are dealing with this subject, but you have developed a very good tool to manage this, especially existing building stock. I could see, is that it? It's reversible building, reversible BIM platform works for the definition of the existing building stock to identify, to classify.
No, it works. That's why I was talking about the 2 tracks and the reversible BIM, which combines the 2. So it is used for the design. If you use a Revit as a design tool, then you can use reversible BIM to assess your design solutions, and using the design guidelines, how to design circular buildings, the assessment of your design solutions using reversible BIM will be better. You will get more circular design solutions. But it can also be used for existing buildings, and we tested that and validated through a number of projects in Europe where buildings were scanned with different scanning techniques. Point clouds are created, and the reversible BIM models are then built up based on the point cloud files. That's of course more time consuming, and when you use it as a design tool, then you are designing using a Revit yourself. You are designing yourself, so you already have your digital model in place. And for the existing buildings, we are building digital models with help of scanning.
No. Go ahead.
Thank you very much, Professor Durmisevic. It was an enlightening lecture, and also the content was fascinating from my point of view. I have a question related to the reversible BIM project. You showed several examples, apartments in France, some museums in Belgium and in Netherlands. I wonder how long does the process take, starting from having a BIM model, or you just go ahead and scan the buildings, and you have how much buildings you have at the moment that you investigated? As far as I saw, it was a part of the research project, and I wonder how fast we can go ahead with the existing building stock.
We have scanned and did a reversible BIM for buildings within the research project, but also beyond. the digital reconstruction platform. I don't know, in total, maybe 15 up to now throughout Europe. And in terms of process, indeed, and then I talk only about existing buildings, not about the new designs. So for the existing buildings, there are maybe 15 in stock. And of course, the reversible BIM uses the methodology which I developed a long time ago. That methodology has been verified during the BAM project. So this is a digitalization of that methodology. And there were many more other cases being done to verify the methodology itself. So we scan the building, and scanning itself doesn't take much time. And then the creation of point cloud files, neither, of course, the creation of digital twin using point cloud files. Usually, I would always ask if there are drawings, it helps. If there is any drawing, like a section or floor plans of a site, it helps a lot to speed up the process. And then, depending on, of course, on the complexity of the building and the size, how much time it would take. Maybe if I talk about kind of typical office building, it would take to get a full inventory. It would take probably 1.5 months, 1.5 to 2 months to get all data out, which I presented today. From scanning to this final outputs and the data.
Okay, excellent. Thank you very much. So we have a question.
Yeah, Esma has the question. Yes, Esma.
Yes, I have a question, and thank you for this presentation. It was really mind-opening, I think, as well. And my question is, and I apologize if you already mentioned, if I missed out during presentation, but you mentioned that you scan the building, existing building, and you transform these scanned 3D points clouds to BIM model. And during this process, how accurate is this? Do you need to modify the elements by yourself and the connections also, or does it automatically recognize whether it's a welded or bolted connection, and how much you need to modify the model?
Yeah, very good question. But the AI is, we are looking into AI with the colleagues who are scanning buildings, and there are some exercises with AI and learning processes taking place, but takes lots of time. So at this stage, we didn't use any AI. There is no recognition, pattern recognition or any form. So indeed, in terms of accuracy, when we get the scan files, then we also get like thousands of pictures, because they are made automatically as well. And as I mentioned, I always ask to get some drawings as well, just to check how things work. So as far as accuracy concerns, I suppose it would go to 5 centimeters, something like that. If I need to be very precise, from 1 to 5 centimeter margin, which might happen if you don't have drawings. So and indeed, so basically the point cloud file is used. You get lots of points, and if you have glass facades, lots of reflection of glass is there as well, especially outside. So that's something I talked with a colleague who's scanning. He is trying to minimize the amount of points, and if you know that surface is a right surface, to eliminate all these noise around these surfaces. But that's all. I know that it is a point of research on many platforms, and I'm sure it will come, but I also know that it takes lots of time to learn AI about one geometry, about one window, one door, that this is that door, and so forth. So it takes time to get there.
Thank you very much.
Okay, any other Barış Korkmaz?
Thank you so much for the inspiring presentation. First of all, I'm sorry I have a problem with my camera. Can you hear me well?
Not really, no.
Okay. The thing is that I also deal with such project as the drawing of hospitals and schools. Last 1 year, and we have many difficulties. We decided not to go with the scanning because there are very too much embedded layers of the buildings. For example, floors in the basement floor of the buildings. There are walls facing with the ground, etc. So it makes it difficult to detect all the layers of the building in such project. So are you also taking samples from the floors or the walls to really get the thickness of layers or the materials, etc. during your project?
We are not taking the samples, but we are taking the inventories, material inventory that is being done in Europe as it is obligatory. If buildings need to be deconstructed, and they make the inventory of hazardous materials and the material specification and the drawings, as I insist to get the sections and the floor plans. Scans but I mean, in combination with the pictures, you can go very far. I have there's a partner for scanning, tries to and does the work quite well, and delivers quite clean and workable point cloud files, so that we can proceed in combination with pictures. And as I said, the drawings, the sections and material specification, we managed to reconstruct the building. And of course, you need to have a architecture engineering background, because when you study architecture, you know that there is a certain development in evolution of methods of construction throughout the centuries, and that's why the year of construction is very important information for us to understand the typology of material composition and techniques that is used at that time. So, to be able to understand better the point cloud files and the combination with the drawings that we get. At this point, that's what we can get out of these techniques, and AI is something definitely that will help in the future when we come to this full pattern recognition files, recognizing the Windows types of Windows producers and so forth. But we are at this moment not there yet.
Thank you very much.
I can only say that usually I've been doing the reuse potential assessments of buildings using the tools which I have developed, and those were Excel-based tools and drawings and so forth. And I had always got to go to see the buildings myself. And I've been doing this for more than 20 years. Since we start getting point cloud files, I didn't have to go to see any of these buildings. So there was enough information to build it up. Of course, besides point cloud files, getting also the drawings. But what was very important in our case is that we get lots of pictures with point cloud files, and pictures and point cloud files, you can map them. And then if there are some questions about point cloud file itself, picture can help identify what you are looking at.
Okay, any other questions? If you don't, okay, we will be quite interesting to try this model within with our work with municipalities, so with students. Hopefully, we will arrange that, Elma.
Okay, see.
Some students will be quite interested to taste it, to identify a building capacity of reversibility. It's very important for us in Turkey, which is this earthquake country, to use this in expanded mode, especially for the existing building stock, to understand what we have and what we could be reused and reversed, reuse potential or recycle potential of this building.
So in terms, what is important in irreversible BIM, I didn't mention that. I didn't mention all indicators, but is the damage of materials. So this visual that we have, there's this parameter visual damage, and that's something that we see on the pictures which are taken when scanning, whether there is damage to the material, and then it's marked as the level of damage which is seen. But as it comes to the real quality of material, of course, there are the labs that need to assess the quality if there's a question about that. Obviously, everything that we can get from the drawings and the pictures and 3D scan, that's information that helps to set up the information about reversibility, so that there is enough information to say something about the reversibility of the structure and the reuse potential in terms of easiness of recovering material without damaging. Whether there is some hazardous content in there, we see that in the reports, if the reports are made. That's usually the case in Europe. So that's how it goes.
Mm-hmm. Okay. Thank you very much. If there is no more questions, we will finish our
Thank you very much.
Again, thanking Elma Durmisevic. We will be following your research and we will be in touch, Elma.
Okay.